Well, hello everybody. Um, Welcome to the very first webinar for Con-Cure. And please forgive me, I'm quite a newbie at this, but I know that a lot of people are working from home these days, and a lot of us are out of the field for good reason. And we thought it would be a really good time to provide some knowledge transfer to our clients and other people that are interested. And so I'm just hoping that everybody is staying safe out there. This series of webinars is really striving to be very educational. These are not sales pitches. If you detect any enthusiasm in my voice, it's just because I'm guilty of being really enthusiastic about maturity and how that can benefit the concrete construction industry so greatly. So the concrete industry currently utilizes concrete test cylinders, and I'm pretty sure that everybody watching would certainly be very familiar with test cylinders. They're made on the day that they're cast. They're stored typically at the job site for the first 24 hours, and then they're taken back to a laboratory. Now, the one thing about test cylinders is, regardless of these cylinders, that due to their much smaller mass, they hardly ever reflect the actual strength of the in-place concrete. This is clearly an issue throughout the entire construction industry, and by the way, it's really the reason that my company exists. And this causes unnecessary delays in the scheduling and higher costs for the contractors. And here's a great example, a real simple example. So this was a picture that I took. You can tell that the contractor did a lot of work with the to protect the concrete, and they had jacketing and blankets and all that kind of stuff. They had heaters running underneath there. But if you look at it this way, the deck was hot and the cylinders were not. The cylinders were actually cured out along the side of the road, and this is clearly an example of where the cylinders do not match the in-place strength. So this is hopefully not the norm, but it's happened before. And so at the end of the day, you take the cylinders back, you break them, and you get a crushing strength. But the difference is, and typically you have to wait until the concrete reaches about 75% of F prime C, the design strength, before formwork stripping or post-tensioning operations can start. But the break testing of these cylinders only indicates the strength of the cylinders. But what about the strength of the in-place concrete? So the reason for this talk is that there is a 30-year-old ASTM standard called Maturity C1074, where if you record the in-place concrete temperatures, that can directly relate to a correlated strength, and the in-place strength of the concrete can be accurately estimated. So that's basically what we're talking about here. You put these sensors in the concrete in different locations, and you can tell what the strength is at those locations. It's already very heavily utilized in the precast industry, and they have to monitor temperatures all the time. The same thing with mass concrete. Mass concrete applications typically require that you monitor multiple locations within that mass, and so that's basically why you have sensors in all these different locations. But anyway, monitoring temperatures is really beneficial for a lot of different reasons. So hopefully this webinar is going to address the whys, the whens, the wheres, and the hows of the different types of monitoring that you might want to do for temperatures. So why do we want to monitor concrete temperatures? Well, a lot of times specs will require it. You can use this information, this temperature information, proactively to, for example, terminate or reduce external heating operations in cold weather. That will save a lot of money on energy costs. That alone should be a great reason for anybody doing cold weather concreting to use temperature probes. But the best use of all And this is something that a lot of people don't know. But if you put a probe in both the in-place concrete and you put a sensor down in one of those little test cylinders at the same time, and you compare the difference between those two temperatures, you will be amazed. It's truly astounding. The cylinders, because of their smaller mass, almost no matter how they're cured, do not match that in-place concrete. Certainly, the times when you should be thinking most about concrete temperature probes being put in your sensor or in your concrete, I'm sorry, it would be cold weather and hot weather conditions, any extreme conditions for sure. Um, Anytime you have a situation where your test cylinders don't match the where you think the concrete is. So, for example, low breaks. This happens a lot with hot weather concreting when the cylinders sit outside in the hot sun. They tend to end up with lower breaks, lower strengths. Obviously, we talked about it, mass concrete for sure. That's always a must. And then for any time-sensitive concrete placements, where knowing that strength of the in-place concrete is important or beneficial for scheduling or logistic reasons like when to strip forms and post-tension. So where should these sensors be placed? That's kind of a tricky question, but generally they can be put in anywhere. If you're just doing temperature monitoring, they can be put anywhere. But if you're doing maturity, you've got a couple of considerations. You want to try to find the thinnest sections of that concrete or the areas that are most exposed to the elements. And also for doing maturity, you want to find the areas of the greatest stresses. So for example, the PT cable heads, the live ends of the cable heads and things like that, or any column slab junctions, places where there are a lot more stresses in the concrete. And then anytime you're doing the cold or hot weather, there are some specific conditions where you need to understand a little bit more about where those sensors are going. Certainly it's sort of beyond the scope of this webinar, but you can definitely you should consider placing sensors, for example, along the edges of the concrete. So how do you do this? It's real simple. There are two different types of temperature probes that are in use today and out in the world. There's thermocouples, that's kind of the old school type, and then there are thermistors. Thermistors are more accurate. I would say most, if not all, of the modern temperature monitoring and maturity systems that are on the market utilize thermistors. They're more accurate, and really the biggest reason is that they don't need to be calibrated every time. A thermocouple is supposed to be calibrated every time you create that thermocouple junction, and I can tell you most people do not do that. Some of the sensors that are out there are sacrificial by design, and others are reusable. You should at least know what your design is. And then the other thing is this isn't just about taking the concrete's temperature at one time. You have to record this concrete temperature. So you have to have some data logger that's associated with this. So some of the data loggers are buried in the concrete and lost. Others are external to the concrete and can be reused. So there's this one extra test. Once you have determined the temperature history of that concrete, you can also calibrate the mix design using strength, using standard cylinders. And as long as you have that recorded in-place concrete temperature history and you have this mix design correlation curve, you can use math to get an extrapolated estimate of the in-place concrete strength. It's a very beneficial process. So if you're already recording concrete temperatures, it's just one more step to getting the in-place strengths. Another good way to look at this is the rate of strength gain of in-place concrete versus test cylinders. So in this particular example, this was an example from a project we did where it was about a 15-story building. we correlated a bunch of data after the fact, and this is kind of the result. You've got a bunch of sensors, give or take. This was sort of an average of multiple sensors per placement. And you can see that they reached the target strength, that's white dashed line there. They reached the target strength in just, on average, about 1 day, maybe a little bit past 1 day, give or take, depending on ambient temperatures and things like that. The yellow line represents the field cured cylinders. So on average, the field cured cylinders reached strength a little bit past 2 days of age. So in other words, they cast them on day one, took them back to the lab, and the next day they would reach that same 3750. So you're saving literally a full day on those field cured cylinders. The black line in this graph represents the mix design submittals. In other words, this is how the mix was actually designed to gain strength in truly controlled conditions of a laboratory. But I can just, this is a great graph because it shows you the difference between the in-place concrete and field cured cylinders, which were, by the way, cured pretty well given the circumstances. One of the other things that you can do with maturity and also monitoring temperatures is you can monitor the temperatures of these cylinders, and you can compare it with not only how the concrete is curing in place, but also with maturity. You can use it to gauge your quality control of your concrete. If your maturity estimates are way off based on your actual cylinder breaks, you know you've got an issue with the ready-mix concrete. So these are some of the major benefits of doing concrete maturity monitoring for pretty much any project. Maturity can shorten construction schedules greatly because of the in situ concrete is typically gaining strength at a much faster rate than the test cylinders. The test cylinders of the same age typically are going to be lower. I should say there are also times when the concrete in the cylinders is gaining strength faster, especially in cold weather, where the cylinders might be placed inside a heated box or a heated cure box. They might actually end up being higher in strength. So again, it sort of works both ways. Typically, though, you're going to be able to stress post-tensioning tendons, cycle your formwork sooner, often much sooner, as I showed in that previous graph. Sometimes it's at least 50% higher. You can reduce the energy usage by terminating external heating operations as soon as the concrete has reached its target strength without having to wait around for the cylinders to get there. That's a big deal. It actually is a really big deal in the precast industry already. And you can save money on your concrete mixes by optimizing mix designs around the target strength times in place, the in-place target strengths, rather than on cylinder breaks. If you're designing all of your mixes based on when the cylinders reach target strength, then then you're wasting time and you're wasting cement. So these are a couple other reasons why the concrete industry in general can benefit so much from maturity. You'll always know the strength of that young concrete, even at very early ages, without having to test a cylinder. Now, you'll still have to test cylinders, but you'll know what your concrete strength is. It does encourage proper curing, regardless of ambient conditions. So, for example, some systems provide real-time data and notifications, text notifications, when the curing conditions approach spec limits, such as concrete that's too hot or too cold. And then this also will reduce the reliance on third-party testing. Most of our contractor customers are doing this testing themselves, and then they rely on the cylinder testing, which must continue, but they can also monitor those cylinders with the sensors, and then it provides a glimpse into how not only is the testing lab curing those cylinders, but it does give you an indication of the difference between the strength of those cylinders and the in-place concrete. So here's a little bit of background on the principle of concrete maturity testing. It's all based on temperature, and it's based on the relationship between the temperature history of that concrete in the field and the maturity index. So actually a better way to describe this graphically. Uh, so if you have for a given concrete mix, if you cure that concrete for a longer period of time at a colder temperature, or a shorter period of time at a warmer temperature, as long as the areas under those two curves is the same, then that particular concrete has the same strength. It has the same maturity and therefore the same strength. So it doesn't matter how you cure your concrete, as long as if you measure this maturity, you'll know what that strength is because of that correlation curve. As I mentioned earlier, there are a bunch of different recognized test methods that are out there right now. C1074 is the ASTM standard. Several ASTM specifications reference maturity. It's a growing list. And so ACI 306 is one of them, 305, the Hot Weather Committee also. And there are quite a few more. A little bit of background on the technical information, and this isn't a screen that I'm necessarily going to read, but there are two different formulas out there. One is called TTF, or Nurse-Sol. It's a simpler formula. It's a linear equation, and it's good for the low risk applications like pavements, where it's not a time sensitive placement. It does assume isothermic curing conditions of that concrete. It doesn't necessarily adequately reflect the strength of the concrete as if the concrete temperatures vary widely. There's another one out there that's called the Arrhenius function, and it's based on the concept of equivalent age. It's a rate equation, and it's a nonlinear equation. So it better accounts for concrete that cures under widely varying curing temperatures and conditions. So most of the time, we focus on using the Arrhenius equation, although many people use either or both. So the only thing that I would talk about here is that the equivalent age is a means of expressing the maturity of the mass or the structure as it relates to test cylinders. And so, for example, if we have if you use a maturity system and it tells you that the in-place concrete has an equivalent age of two days, that concrete will have the same strength as a test cylinder cured under controlled conditions in the laboratory for 2 days, regardless of the actual age or the curing conditions of the in-place concrete. So the concrete could be 1 day old, but if it has an equivalent age of 2, it will be the same strength as a 2-day-old cylinder in the lab. So if we know the strength of that 2-day cylinder, we can estimate the strength of the in-place concrete. So I did have one customer who initially had a little bit of trouble understanding equivalent age, and at the end she said, "Oh, I think I get it. It's like dog ears." So you can have concrete that is acting like it's either younger or older than the actual age of that concrete. So think about dog years, like 7 years, that kind of stuff. So there are some requirements for doing successful maturity testing. You need to have consistent concrete batching. If you have concrete that is delivered to the job site that is varies from truck to truck by a lot. So, for example, one truck has a 4-inch slump and the other one has a 9-inch slump, and nobody really knows exactly why. Well, you have bigger problems than maturity testing can solve. You need to get your concrete batching down. You also have to have adequate hydration. In other words, you can't have concrete that's either too dry or dries out during the curing process. You have to have enough moisture in that concrete for the hydration process to take place. You have to make sure that you're putting the sensors in the right locations. You can't just put a sensor smack dab in the middle of a 2-foot beam that's super large and expect to know what the strength of the thinnest section of that slab is. You have to make sure that you're putting the sensors in the right place. You have to also correctly interpret the temperature and the maturity graphs that are provided by your maturity system. I will say that in this day and age, a lot of people want to have just a push button answer. They want to push a button and have their maturity system tell them that they've got 2,900 psi or something like that. I have always said that you have to take a look at that temperature graph to make sure that it makes sense. And then I also think that you have to have validation of your maturity curve and validation of the test results. You can't just blindly consider the strength being 3,000 psi and just trust 100% that maturity system is 100% accurate without verifying that using some cylinders. It doesn't mean that the cylinders have to be also 3,000 psi. So as an example, you could have a maturity that says your in-place concrete is 3,000. But if you have a sensor inside a cylinder and you test that at that same age, as long as the maturity estimate of that cylinder is the same as the actual break of the cylinder, then that's considered a valid result. I hope that makes sense. So there are three basic procedures or steps to making to doing maturity in the field. The first is you make a maturity curve. The second is you obviously test in place, put the sensors in, and the third is you validate using the cylinders, which we just mentioned. So clearly, the most important step is to determine the calibration for maturity. We call it a signature strength maturity curve or an SSM curve. We don't really use that terminology anymore. That's what we used to call it a long time ago, but I still have people that refer to it as that, and that's good. So what you're going to do is you're going to create a maturity curve for each mix. This is mix specific, and you're also going to possibly, ideally, create a maturity curve for each mix variant where different amounts of admixtures are used. The curves should be validated periodically, particularly, and this is required by ASTM, if the source of the constituents changes. So for example, if you have a mix design and the aggregate source changes from one quarry to another, you really should at least validate the maturity curve. So the way you do this, the way you make a curve is you're going to have a production batch of the exact mix to be tested, 3 to 5 cubic yard minimum batch. You can't do this with a tiny little lab batch. You're going to cast 18 to 21 cylinders of that mix. You're going to, and obviously make them properly, level them out, all that kind of stuff. You put a sensor down inside at least one of the cylinders, and you will launch and attach a maturity meter to that. There's an actual picture. This is from a long time ago. That's our original black box maturity meter. They've come a long way since then. But you're going to cure those cylinders in a moist cure environment per ASTM. So you want to make sure that it is a controlled environment. It doesn't really matter what temperature you cure them at, as long as they are cured at the same temperature for the entire period. So the most common is lab temperatures, 21°C or 73 degrees Fahrenheit, and 100% humidity. However, and this is a big however, if you're doing hot weather concreting, precast and elevated temperatures and things like that, it would be better to cure these cylinders at a higher temperature, at a temperature that is close to, or it doesn't have to be exact, but fairly close to the temperature that is expected in the field, the average temperature. So definitely there are times when curing these cylinders at 70 degrees or lab temperatures isn't the best thing to do, but a lot of my customers will cure their cylinders at maybe 90 degrees. Literally put them right in the water bath at 90 degrees. So what you're going to do is you're going to schedule the breaks to occur well before and after the target strength is reached. So for example, 2 sets of breaks prior to your target strength, and then 1 set of breaks around your target strength, and then the rest of the breaks can be spaced out. So for example, if you've got a 3-day mix. You expect your strength to be reached in 3 days. You would break cylinders at ages day 1 and day 2. Those would be the early breaks. And then the day 3 break would be around that strength. And then to finish that out, a 5, a 7, maybe a 14-day break. You really don't have to go out that far. 28 is pretty optional. Most people don't even have a 28-day break on their maturity curves. If you have a concrete mix design where it's gaining strength very rapidly, like a pavement patch or precast, you might be talking about hours here, not days. So you're going to break 2 at each age, and this is important, 2 at each age, and record the average of those 2. If the range between those 2 breaks is greater than 10% of the average, you're going to break a third cylinder, and you throw away and discard the results of any obviously defective sample. So as an example, if you have your first break of your testing is, let's say, 2000 psi, and the next break is 1000 psi. Well, the range there is clearly 1000 psi, but the difference between the two. But the average is 1500. Well, those 2 cylinders are too far apart. It's the range is greater than 10% of the average, so you then have to break a third cylinder. And if you then break a third cylinder, and let's say that cylinder breaks at 2100 psi, you can use those 2 breaks, the 2000 and the 2100, and you can throw out the obviously defective low break. You're going to enter all of this data into your software. Whatever maturity system you have, there's all sorts of different types of ways to do it. You're going to enter the ages typically. You're going to enter the strengths. You're going to have the mix design, all sorts of other information that is provided to you. Sometimes you'll either have a specified temperature or you'll have a TTF number that you're entering also. So once you have that done, you've got your maturity curve and you can implement that out in the field. So these are some of the barriers to acceptance of maturity that we encounter pretty much every day. We find that there are a lot of engineers that are unfamiliar with the benefits of getting that in place maturity data, and they rely entirely on cylinders for strength determinations. I think that is short-sighted, and for whatever reason, they have a refusal to allow or even accept maturity as an additional means of strength assessment. We can help you if you're out there and you need engineers to come on board. We can help you with that because I talk to engineers all the time, and they understand that what they actually really want from this is the strength of the in-place concrete, not the cylinders. We come across a lot of contractors who are unwilling to fully embrace the maturity testing process. There definitely should be somebody at the company or for your crews who knows what they're doing about maturity. It's very helpful because there are some things to know about it, but it's really helpful once you know it. And I will say this, and this is also important, that poor quality control of the delivered ready mixed concrete is a huge barrier to maturity being successful. If you have drivers that are adding a ton of water when they shouldn't because the slump is changing as they're driving, that's bad. You really have to control your water. If you have a project where you're dispatching 15 trucks to a large project and 14 of them are sitting in line for an hour and a half to offload their concrete, again, these are real issues for any maturity, any accurate maturity results. And certainly the instability of air entrainment and slump from batch to batch, and even during placement, such as if it's pumped, concrete being pumped, it can cause a wide variation in test cylinder results. And you have that's really an issue for the concrete industry to address. And finally, of course, there are people who just don't understand maturity and they make mistakes. And there are failures that are due to the improper use of the maturity test in the field, which is why we provide a lot of training for our customers. But I would really like to thank everyone for attending. As I said, it's the first one. Maybe we'll redo this later with a little smoother outcome. I hope. I don't know. But anyway, really thank you for your time. Hope you can join us. The subject of the next one, as you can see there, would be extreme weather concreting, and that's hot and cold weather concreting, and all of the various issues that come up with that. It'll be a little shorter. We're going to talk a little bit about how maturity can benefit that too, but mostly it'll be just sort of best practices. So thank you very much, and I appreciate everyone's attention. Have a great day, folks. Bye.